We're going to look at the average power with a sinusoidal current source applied to a 100 ohm resistor. We're going to look at the average power delivered to the resistor. We're going to sketch the current waveform, and we're going to sketch the power waveform as functions of time. The circuit that we're given is a current source connected to a 100 ohm load. The current source, I of t, is given to us as 10 times the cosine of 2000 pi t. Let's start off by sketching the waveform for the current. We need some additional information extracted from this cosine term that's been given to us. We need the peak value, 10. We need the phase shift, theta, in this case 0. And we're going to need to be able to determine the period of the waveform from its angular frequency given to us in radians per second, or omega. We can find the period by finding f and inverting it. So omega is given to us as 2000 pi. F is equal to omega over 2 pi, or 1000 hertz. And the period of the waveform t is just 1 over f, or 1 millisecond. So now we have everything that we need to be able to sketch our waveform. Draw our axes. The horizontal axis is going to be time in milliseconds. We're sketching I of t in amps. Our peak value will be 10 amps. The peak inverse value will be minus 10 when the cosine goes to minus 1. There's no phase shift, so we're going to start at the peak value, go through 0, hit our inverse peak, back through 0 again, and back to the peak value, and it's going to do all of that in 1 millisecond. We can go ahead and draw our waveform. The easy way to find the average power for a resistive load, P average, is to take the RMS current, square it, and multiply it by the resistance. In this case, because we've got a sinusoidal waveform, the RMS current is going to be the peak value divided by the square root of 2. So that's 10 divided by the square root of 2 squared times our resistive value, 100, for a grand total then of the average value, 5 kilowatts. A little bit more rigorous way to do the average power, and we're going to have to do this anyway because we have to sketch the power waveform as a function of time, is to go ahead and start with the basic relationship for power. That's the voltage waveform, V of t, times the current waveform, I of t. To find the voltage, we're looking at the voltage across the resistor, V of t. We can find that with Ohm's law. That's going to be the current waveform, 10 times the cosine of 2000 pi t, times the resistance, 100 ohms. That's our voltage waveform, V of t, times the current, 10 times the cosine of 2000 pi t. I of t. Do the arithmetic on this, and we should end up with 10 to the fourth times the cosine squared of 2000 pi t. I'm going to refresh your memory on a trigonometric identity that tells us that the cosine squared of theta is equal to 1/2 plus 1/2 times the cosine of 2 theta. If we apply that to the relationship that we've got over here, we're going to end up with 10 to the fourth times 1/2 plus 1/2 times the cosine of 4000 pi t. Or 10,000 divided by 2 plus 10,000 divided by 2 times the cosine of 4000 pi t. So here's our 5 kilowatts average value again. 5,000 plus 5,000 times the cosine of 4000 pi t. The average value of this term is 0, and all we'll have left is the constant term out front. Now, in order to sketch this, we're going to need to figure out what the period of our new waveform is. The angular frequency is 4000 pi. The frequency in hertz will be 2000 hertz, and that gives us a period for our waveform of 1/2 millisecond. The peak value will happen when the cosine term goes to +1. We'll have 5,000 plus 5,000 for a peak value of 10,000. When the cosine term goes to -1, we'll have 5,000 minus 5,000 for a minimum value of 0. So we're ready to go ahead and sketch our waveform now. Here's t in milliseconds. P of t in watts. Our peak value, 10 to the fourth. Our minimum value, 0. And that kind of makes sense if you think about it, because we really can't have the power and the resistor going negative, because that would tell us that the resistor is delivering power out to the rest of the circuit. And that's something that we really would rather not see. So we're going to go through 5,000, hit our minimum value, back through 5,000, and back up to our peak value again. And we're going to do that all in 1/2 millisecond. There's our average value. And that, I think, is about everything that you're going to need to know about the average power in resistors.